So we are going to make the introduction of this webinar. And so who are we? Who are iBTest? So iBTest is a Mexican supplier on specialized back to front-end electronics in manufacturing. We are solutions and services, and we also help our clients to discover the new trends of technology by creating turnkey solutions for automated test equipment and customized automation environments that are effective, flexible, agile, energy efficient, and safe. And we are working side by side for all customers, many included in the NASDAQ index and Fortune 1000 companies. And who's Acroname? So they make automation products for over 25 years. They are experts in test and also automation. And they make tools for test engineers. And probably you have used one of the products that they test that are tested by Acroname tools. And we have the sales support team also from iBTest. We have a Daniel, and in the Acroname team we have a Lance. If you have a commercial question, you can also say to us because they are present here in the webinar with us. And well, who's Mitch Nelly, our speaker for today? He's a senior software engineer. He has been part of Acroname for 5 years. He has 12-year experience on system design engineering, precisely in safety systems, data acquisition, and product development. And he's also a technical lead for Acroname product firmware and software. And he's also an author of Acroname's Brainstem, LabVIEW API, .NET API, and Steam tool application. So everyone knows that I leave you in good hands. So please welcome to Mitch Nelly.
Awesome. Thank you for that introduction, Rebecca. Hopefully everyone can hear me here. I think I'm unmuted. Welcome to the MicroFCT revolution, everyone. Today, we will be showing you a new approach to functional test systems, MicroFCT. We'll start off by talking about the philosophies that make up the MicroFCT concept. Then we'll take a look at some specific examples of applying these philosophies and the amazing results that can come from the MicroFCT design approach. We'll see an automotive USB-C hub, a point of sale system, and a test system for test equipment. Finally, we'll check in that we're keeping our bosses happy and look at a development schedule and costs for MicroFCT fixture design. Let's dive in. So most people probably don't think philosophically about manufacturing test, but I'm not one of those people. And if you're on this call, you're not one of these people either. So now you might not be thinking you have a philosophy for functional test design, but you really do. Your philosophy is embedded in the goals you have for your design and the strategy to achieve those goals. The goals of MicroFCT aren't new. It's what we always wanted, and it's just like everything else we want. We want it faster, cheaper, and better. But more specifically, we want shorter test times, lower equipment cost, easier development processes, faster replication, less time at the CM deploying, and less downtime. The hard part of getting all these at the same time. MicroFCT introduces some simple philosophies to direct your test system development to get you closer to these goals. When designing a test system, we should think about answering the question, do I ship this product or not? Of course, we also need some parametric data for process control, but our goal as test system designers is not to provide failure analysis information. Our job is simply to say ship or no ship. We should think inside the box and in more ways than one. First, we should think about getting all of the test equipment inside the box. That is, inside the test fixture. If we can do that, we get faster replication, easier deployment, less downtime, and a far smaller footprint, which will make our CM very happy. While developing our test methods, we should also think inside the test equipment box. We shouldn't just accept that an off-the-shelf piece of equipment is the best way to perform a test. We should think to ourselves, how would I do this in the lab manually? What equipment would I use? Then think, how does this equipment make the measurement? Can I do it differently in an automated way? Keep in mind that the best way to perform something manually is rarely the best way to automate it. We as test engineers need to adapt and adopt this concept in our profession. Look to test the critical functions of a device. Any good electrical engineer will admit that many of the component values on a product are just best practice or rule of thumb. So why should we measure every component on the board? Besides, the days of wrong component stuffing from leaded components are long gone. Thankfully, surface mount technology has saved us from this. So instead, look to functionally testing the critical features. If there's a wrong or missing component and it matters, it should show up in the functional test. Remember, we're just going for ship, no ship. We're not trying to do a full validation, generate eye diagrams, and check firmware features. We just want to know if this device was put together correctly. Too often as test engineers, we simply don't have the time to learn the standards associated with things like testing. But there is a huge advantage in doing so. Instead of buying expensive test equipment designed for validation, which can be hard to automate at scale, we can design a system with the right equipment to verify functionality. As I said, the design has already been validated. We just need to make sure it was put together correctly. As with any job, it's imperative to remember who the customer is. Sure, you might have a contract directly or indirectly from an OEM to develop the test system, and the OEM is likely paying your check, but they're usually not the one running the test system. In many cases, the OEM hasn't even put much thought into the production process, much less the test process. So we all know how it goes. The OEM just specifies the exact system they use for validation and then asks us as test engineers to automate it. And of course, meet a whole bunch of other goals as well. Since the CM is the one who will be running the test system, they will be the ones who call us when things go wrong. They are the real customers. So as we design their test system, we need to consider what they need. Small, even portable test systems that don't fail, deploy quickly, and can be replicated at a moment's notice. These philosophies together are what make MicroFCT is all about. These are the strategy to meet the goals we've always had. MicroFCT is about creating systems which are truly optimized for manufacturing test. Sorry. Of course, a big part of any test system is the test equipment. Typically, as test engineers, we start with the test equipment and then build automation around it. However, we need to ensure that the test equipment aligns with our philosophy. As we've been discussing, the goals of MicroFCT are not new. There's been a push for test equipment targeted at manufacturing for a long time. We're all trying to do better than the big iron test systems offer. There are many options out there, and of course, PXI is the go-to standard. PXI definitely hit the mark by being modular, having reasonably good density, and in most cases being very high quality, which you will pay for. In many cases, even the PXI chassis costs more than the customers are willing to pay. So to save money, many people look to low-cost microcontroller platforms like Adrenos or Raspberry Pis. They are very low cost, but they are very difficult to replicate and scale a production process with. These are hobbyist and educational tools, which are just not robust enough to depend on in a manufacturing environment. As we move from right to left in this diagram, we are able to reduce our cost, but it comes at a price. To make progress towards the goals of MicroFCT, we need a test equipment platform that is thinking the same we are. Low cost, targeted at manufacturing, reliable, reusable, scalable, and small but dense with features. That's where Acroname's manufacturing test modules come into play. MTM is a new paradigm of test equipment to go with the new paradigm in manufacturing test system development. MTM is optimized for the manufacturing test. It is low cost, reliable, reusable, scalable, and small. Best of all, it enables MicroFCT design approaches through careful selection and grouping of features. One of our customers told us, using PXI is like hunting with a bazooka. It's effective, but you won't be happy with the results. And MTM is a new approach. It is not overkill. It is specifically designed for the task at hand, manufacturing test. MTM gets you closer to your measurements. It offers modern APIs with a low-level interface to simple protocol. This makes for radically faster response times. Normal measurement processes for SCIP or PXI instrument is measured in seconds. MTM modules provide consistent response times in 1 millisecond. And since every MTM comes with a built-in RTOS, things can go even faster than that. MTM offers simple modules with logical, useful groupings of functionality, allowing you to build test systems with diverse measurements without hacking and taping incompatible systems together. And MTM is very small. Remember how the CM is our true customer? To the CM, floor space is money. If you can reduce the floor space needed by the test system, the CM can offer more test system services to more customers, which means you've got to get out there and design more test systems. Smaller really is better. So how small is MTM? It's very small. On the left are the traditional big iron testers. These are the J750 dinosaurs that your CM hangs onto because they spent so much money on them, they feel that they just have to keep them around. Or they're custom design racks or benchtop equipment taped together into a test system. These are the ones you get called to fix after the person who designed it has left the company or simply stops answering their phone. PXI was supposed to be the answer to all these problems of the big iron testers, but it seems PXI lost sight of the dream. They ended up being too expensive and almost as big. Using MicroFCT philosophy and test equipment like MTM, we can build test systems which are truly desktop with all the test equipment inside the fixture. Here's a real example. These two test systems are to scale. It's hard to capture the scale difference because the difference is so fast. But this elephant should definitely be scared of this mouse. There are real examples of systems which test consumer USB devices by powering the DUT, flashing firmware, testing USB functionality. They do a lot of the same things. One just does them in a MicroFCT way using MTM. What you are not seeing on the left is all the wire wraps under the fixture, which go to test interface blocks on the back, and the 6 or more ribbon cables running down to the test equipment. And what you're not seeing on the right is any need for external racks of equipment, interface blocks, or wire wrapping. All of the test equipment is inside the fixture. Let's take a look. With MTM, small size, and optimized module functionality, we get all of our test equipment in the mechanical fixture. No wire wraps, no test interface adapters, no ribbon cables. In fact, MTM modules implement a simple backplane for networking between the modules. So there's only one USB connection to the whole system, regardless of the number of modules. Now, to address the specific question of attending, technically there is a limit. It's about 15,000. And if you're using this many modules, you're doing something wrong. That's what's possible when you think inside the box. All of this equipment inside the box. So let's take a look at a real-world example. The first one comes from our European test service partners. They were contracted by a major tier 1 OEM for a luxury German car brand. They were to build an end-of-line test system for a USB hub that had a USB-C connector. This is a very simple device with a relatively straightforward test plan. To reinforce some of the MicroFCT philosophies, let's walk through a design approach. On the right is a simplified test plan. Open short checks, voltage checks, power loading, USB data. Very simple. Remember, MicroFCT says we should know the standards we're trying to test. Knowing the standards is what allows us to know that testing USB functionality will give us test coverage to BC 1.2 and the other mobile phone features. So I don't need specialized test equipment for those features. For now, let's just focus on the open short checks of the USB-C port. If you are not familiar with the USB Type-C connector, it is quite dense compared to most consumer electronic connectors. It has 24 pins with a very fine pitch. This makes it very easy to create solder bridges, resistive shorts, and opens due to bent pins are very common. Since the connector carries both power and data, a short could end up being very damaging and expensive if it makes its way to a customer. First, let's think, how would I test this by hand in the lab? Well, we'd start by getting a USB-C breakout board, grab our trusty multimeter, and start probing all the possible pairs. There are 24 pins, so there are 576 permutations. We could be here for a while. However, we're smart engineers. We know that direction doesn't matter for open short checks, so we're only looking for combinations. That gets us down to 276 measurement. Look at us, we're saving time and money already. However, this is still going to take us a long time to do this manually, and our customers would really enjoy making a profit. So we need to automate this process. No problem. I've got lots of multimeters and an unlimited budget. Now, obviously I'm joking. No one would do this. This is absurd, but let's go down this path and see where it leads us. Now, because we know the USB-C standard, one of our philosophies, we know that some of the pins are shorted together, like ground and V-bus, so we shouldn't have to check those independently. Awesome. But wait a second. This product is pushing rather high currents, and it's an automotive device, so reliability is counting on all the ground and V-bus pins to actually be connected. So we do have to check them after all. But like I said, no one would actually do this. A more realistic approach is a multiplex the multimeter's input leads. In fact, I would be willing to bet that everyone on this call has seen or even designed something just like this. So what we've done here is traded a fully parallelized set of measurements for sequential measurements. That is, measurements spaced out in time by changing the connections to the multimeter via relays. When I had hundreds of multimeters, I could check all the open shorts on one connector in a single time slot. That's assuming a bunch of DMMs linked together would actually work. And I'll give you a hint, it doesn't. But now that I'm checking one pair at a time with my one multimeter, I did save lots of time and money, or lots of money up front, but at a cost of time. Now, how much time? If we assume a half a second for relay settling and a half a second for multimeter readings, we hit 5 minutes really quick. Ouch. Can we do this better? What does MicroFCT teach us? Think inside the box. How does this magic box work? How does it make an open and short measurement? Open and short measurements on a DMM are typically the same as resistance measurements. The only difference is that they have defined a threshold for one or the other. If we are below the threshold, it's a short. If we're above the threshold, it's an open. These resistance measurements are made by using a current source and then measuring the voltage created by the unknown resistance. A little bit of Ohm's law and boom, the resistance is determined. However, if you've ever messed with the current source, you know that designing one isn't very easy. But with a little bit of electrical knowledge, we can create an equivalent circuit using a voltage source and a resistor. Now, let's take a look at how we can start applying this circuit to our open short checks on the USB-C connector. So here I have a simple voltage source going through a simple resistor connected to a USB-C connector on my DUT. If there's a short, current will flow from the shorted pin and return to the voltage source. All I have to do is measure the voltage generated. Now, if you're paying attention, you see I was a bit tricky here. Instead of just one resistor like I had before, I split the resistor between two terminals on my multimeter. This is something I just can't do with the multimeter off the shelf. Now, it complicates the calculations a little bit, but as far as electrical calculations go, Ohm's law is pretty straightforward. And by adding the extra resistor, I've created a very simple voltage divider network. If the measured voltage equals my source voltage, then I have an open. If I get half my source voltage, I've got a short. Now, why would I split this resistor? Well, remember, we're thinking inside the box. The multimeter can't split the source resistance, but we can. And by doing so, we can check multiple pins at once. Check this out. By splitting the resistance, I can now determine if a pin is shorted to not just one pin, but to two pins. You see, the circuit will generate 3 different voltages for the 4 possible outcomes: open, 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 short, short, open, and short, short. And I can do this for any number of pins, like 24 of my USB-C connector. In other words, I'm able to test the continuity from one pin to all other pins in a simple measurement. Remember those 276 test cases? I just did 24 of them in a single measurement. If it hasn't yet, your head should be exploding. And those pesky pins that I expect to be shorted together, no problem. Not only can I tell you that they're shorted, I can tell you how many of them are shorted. This wouldn't even be possible with the normal multimeter. And now in this diagram, I even show the next step of all this. For the voltage source, I can use a simple digital IO driving high on the positive side, and then an IO driving low in return. And that voltage measurement, a simple ADC will do it. All I need is one IO and one ADC per pin. No relays, no multimeters. Now, I still can't do all the measurements simultaneously, but I can do them 24 at a time, walking through each pin, driving it high, and pulling all the others low until I've tested all the pins. Now, all this can be done via an MTM DAC and MTM USB stem module. Now we're saving some serious time. If we go back to our traditional setup, we were looking at a test time of 5 minutes just for the connector. Using the MicroFCT approach with MTM modules, we can reduce that to less than 1 second. The difference in time was so vastly different to what our customer expected that they were initially not even happy about it. The test is too fast. The customer is not going to believe it's making all the measurements. Well, you know what? They got over it. So the test system is too fast. It's cheaper, it's smaller, and the system is more reliable because I don't have any mechanical relays which are prone to inconvenient failures. There's one other MicroFCT philosophy I'm following in this example. Did anyone catch it? Remember, we're testing functionality, not validating. The traditional approach will tell us exactly which pin was incorrectly shorted, but that information comes at a cost we will pay for with every single DUT we test, a cost of 299 seconds per DUT. Can you afford that? The MicroFCT approach can't tell you which pin is shorted. All it can say is that there's a connection that shouldn't be there. It will then be the failure analysis engineer's job to figure out what went wrong. However, an FA engineer is unlikely to troubleshoot such a high density connector like this. They will simply send it off to have its connector replaced and the board retested. It's only the third or fourth failure in a row when an FA engineer will really dig in. So in this simple example of open short testing a USB-C connector, we played all but one of the MicroFCT philosophies, and it resulted in a huge cost and time savings. Interestingly, we'll never even talked about the CM, but what we ended up with is going to make him very, very happy. So I think we get credit for all 5. Now, I'm not going to dig into nearly as much detail on these next ones, but I want to highlight some of the interesting approaches. This next example is a point of sale system, so a credit card reader that you would see in any store. The hard part of this requirement on this product was that the customer had developed custom ASIC processors in order to bake in the security features. This made it so that the DUT would only communicate with devices of the same silicon. This challenge led us to use what we call simulated build test. That is, you put all the parts of a fully assembled device into the fixture. On the right, highlighted in yellow, you can see the customer's components we had included in order for the devices to function properly. These pieces weren't necessarily being tested, but in order for the system to operate, they needed to be present. These items are 2 magnetic read heads and a control board. The interesting consideration here is to ensure these known good components don't get damaged by a bad DUT in the fixture. As such, one of the big jobs of a test system is protecting the test equipment components. Further, to enable easy replication, these components needed to be super easy to install. We took great care to ensure these could easily be snapped into place. And the customer CM was able to replicate this fixture nearly instantaneously because of that. In the middle, you can see one of the other complications of this device. It had all the test points on the bottom except for 2, which were high-speed USB 2.0 lines. We routed these USB 2 signals to pass-through probes up to a set of top plates. We used a rigid guide pins in the bottom plates to ensure alignment between the top and bottom plates. The reason we were able to do this is because the MTM IO serial, which is a programmable USB hub, is able to boost the USB signal to the upper plates through the poor impedance matching of the pass-through probes. So we didn't have to run a second USB cable to the top plate. On the left, you can see the final fixture, which has all the test equipment inside the box. The only thing the CM had to provide was 2 external DC power supplies and a USB connection. This system replaced a previous system that had died unrecoverably 4 times in the first few years of production. This product is now nearing end of life, and the MicroFCT fixture that we provided has been running for the past 4 years without issue. Now that's reliability. Again, I'm just going to touch the highlights here, but this example is a test and development product. It's actually a CAN bus interface for automotive testing. This product had been tested using a manual test process for many years. And because of that, the customer always had higher than desirable return rates and finally decided to automate the test process. When we first spoke with them, they were investigating a traditional test system using a multimeter and a lot of relays. Does this sound familiar to anybody? Luckily, we were able to talk some sense into them. And after learning about MTM and the MicroFCT approach, they had us build this. On the left, you will see one step in the manual process. At this point, the operator had to toggle these switches and make sure the LEDs were the right color and that they changed properly. Not only did we automate many of their manual test processes, but we also automated the LED tests by using a color analyzing circuit connected to an MTM USB stem. With that, we were able to report brightness and wavelength. And since the system is monitoring the DUT's power consumption, we could even determine the LED's efficiency. So let's briefly touch on assembly here. If you remember, one of the goals of MicroFCT is fast replication. In designing these test systems, we consider ease of replication in every step and every part. You can see a remarkable resemblance between all the systems I've shown, and for good reason. This style of test system can be replicated very quickly and inexpensively because of its modular nature. This is Jackson. He's an intern at Acroname. He built and validated 3 test fixtures in a single afternoon. He got to go home early that day. Okay, another quick example. Here's a look at a customer's laser cutter control board test system. Now, this one was really interesting for a lot of reasons, but I can't really talk about them too much. However, this is what we replaced. Here's some more fixtures we replaced. These guys all had good intentions, but sort of missed the boat on execution. In the end, these customers are very happy with their new MicroFCT MTM-based test systems. Here's a bonus example because I faked you out on the last one. Let's go big with this one. It's a panel level test for a flexible circuit board as the DUT. If you look closely at the picture in the center, you will see the DUT. But what you may not notice is there's actually 16 DUTs in this fixture. In fact, all the DUTs are still connected by their flexible circuit boards. In this particular case, the DUTs needed lots of signal conditioning that you can see on the right. To make things more difficult, the customer had already written a lot of complex code for a very specific NI DAC, and they wanted it to be used during the test. No problem. Although we have left the wire wrap world, the world has not left wire wraps. Using our MTM ribbon cable interface, we were able to seamlessly integrate the NI DAC. And since Acroname provides LabVIEW API, the software could also be easily integrated. In this example, the MicroFCT philosophy enabled the customer to do panel level testing. Their previous test systems took an entire rack of equipment for a single DUT at a time. Here, MicroFCT and MTM put 16 DUTs with equipment all inside the fixture. So that's a bunch of real world examples of MicroFCT test systems. But do all these take forever to design? Do they cost a fortune? I hope you know what I'm going to say here. Simply, no, they do not. In fact, MicroFCT design systems are generally simpler to design. So they're faster to create, faster to assemble, and faster to deploy. Let's look at the cost breakdown for test system design. Now, many test providers had to play games with the total cost of ownership by using high costs for operators in order to show their test automation saves money. With MTM, there is no game. It's because we're in a completely different league. I'm not making this up. These numbers are from Averna's website. Here's the link. I've taken their numbers and added a units per hour, UPH, and a cost, unit per H, column. For the sake of UPH calculations, I'll assume 3 shifts for 18 hours a day, 5 days a week, 50 weeks per year. For the manual station, the UPH seems low considering the high fixture cost. And I can't really defend Averna's numbers here too much, but in my experience, a decent manual tester can hit 10 UPH with good fixturing, uncomplicated process, and good operator training. But let's just trust Averna here a bit, but keep a factor of 10 in the back of your head. The traditional test system shines in both NRE and recurring cost. And of course, we see a 20x improvement. And look at that, it's even cheaper. Now, let's add the MicroFCT test system. For the MicroFCT test system, I'll use the test times from the automotive USB hub example we discussed earlier. This system can do a batch of 5 units in about 30 seconds. Now, for NRE, I think 20K is a bit on the high side, but I'm not going to get too picky here. I'll just stick with Averna's numbers so we can play fair. But the real difference comes from the recurring cost. I'm not sure why Averna's recurring costs are so high here, but I assume there's high equipment, replication, and deployment costs built in. And that's where MicroFCT and MTM stop playing the same game and start its own league. The MicroFCT test system is 20 times faster and 10 times cheaper per system compared to the traditional test system. The MTM test system is even cheaper than the manual line fixture. On a cost of unit per hour basis, the MTM system has 100 times more output for your test dollar. That is, units tested with MTM in a MicroFCT test system have just 1% of the total test cost compared to traditional automated systems. So which league do you want to play in? So just so you know that I'm not playing fast and loose with these numbers, I'll show you an example breakdown from the CAN bus adapter example I showed earlier. The NRE for this system came in around 18K with US-based engineers. The customized fixture was about $500 for the custom PCB, and the MTM modules were only about 2K. And assembling the deployment times right at 1. That brings the total recurring cost per fixture to just under $6,000. Totaling everything up, that brings our fixture cost to $30,000. Replicating to 5 fixtures brings that down to under $10,000 per fixture. And you see that the MicroFCT test system can be designed and built in 6 to 8 weeks. And since replication is so fast and easy, it almost always makes sense to build more than one. Even if you don't need the throughput, take 2, they're small. And when you need to scale product up, grab the extra fixture off the shelf and plug it in and start printing money. So why are these recurring costs so high? And without knowing Averna's exact calculations, I can't be for certain, but I do know how much traditional equipment costs. If we break down the test equipment needs for a simple fixture, we start to see where all the cost is. And a representative set of MTM modules totals just under $2,000. That's less than an empty PXI chassis. So if you're still paying $75,000 per fixture, you're in the wrong league. And welcome to the MicroFCT league. Now that you know what a MicroFCT system can bring you, what's the process for actually making a MicroFCT test system? Well, the design process is very similar to a traditional design process with just a slight tweak in philosophy and strategy. Now, these are actual videos of our design process, but that's a discussion for another day. For now, you know the experts who know how to do this. Many of them are on the call right now. Reach out to Acroname or to our wonderful partners, iBTest, to learn just how you can join the MicroFCT revolution. If this topic is something you'd be interested in learning more about, please let us know, let iBTest know. The better response we get, the more we can bring you content like this. In the meantime, thanks for your attention, and I hope this was a helpful look at MicroFCT, a new approach to manufacturing test system design. All right.
Thank you, Mitch, for your presentation. I don't know if Anyone have questions for the public? Don't be shy.
Hello, Mitch.
Hello.
And thank you very much for your presentation.
Yeah.
Question. You have one slide with the different kind of Acroname models that we can use for a micro FT.
Yeah, let me grab that slide real quick. So here's our entire product offering. You can see we have everything from our newest board here, which is a load board for testing, motor controllers or our high current outputs. Our I/O serial board, which is a USB hub, general purpose modules, relay modules, programmable power supplies, and a very dense analog DAC card. Does that address your question?
Yes, really, thank you.
No problem.
And I have another question. Have you ever used Acroname controlled by, I don't know, by a Linux PC or a Raspberry or a Lada Panda, those kind of devices that we can, that they are like a CPU in a little environment?
Yeah, so we provide APIs, communication to these modules for in both C, C++, Python, .NET, and LabVIEW. Additionally, all these are all available across Windows, Mac, and Linux. And we even go as far to create very specific distributions across numerous Linux processor types. So 64-bit, old school, 32 bits. We have ARM 7s, ARM 6s, ARM 64s. So I guess what I'm getting at is software is never going to be your problem with us. We've got you covered.
Oh, that is grateful, Mitch.
Mm-hmm.
That can help us a lot with the controller for the test.
Yeah, and please, you can take a look at our webpage. It's acroname.com/support. And all these APIs are fully documented in our reference page. So if there's any function you're interested in, they're all there.
Okay, thank you, Mitch. I will check.
Good.
This is Adolfo. I have a question.
Yeah.
First of all, thank you for the presentation. It's really interesting.
Yeah. No problem.
And I'm thinking, my question is regarding if you are using, or do you know, in some location of Mexico, some company is using these MicroFCT modules at this moment. Whereas we are located in Guadalajara, it's the same city that iBTest is located. So yeah. I'm interested in that.
Yeah, absolutely. We're using these modules all over the world, including iBTest has designed these into fixtures before. So like I said, they're going to be a good resource for this kind of fixture design. But they're there, and furthermore, if you have a product with a USB connection on it, at some point they've probably used one of our products. We're kind of just behind the scenes here, but they are very robust. And like I said, they're just made to be in the manufacturing environment. They're very durable.
All right, and also I am excited because in some of the part of your presentation, I can see Ingun test feature, manual test feature. So yeah, that means we can work together.
Yeah, we really like Ingun, and really because it matches with our kind of design. Like everything here, all our modules are plug and play. They just snap in and out. Well, that's kind of how Ingun is too. I mean, we do a little bit of machining to get our test point carrier board correct, but we can just buy these things off the shelf and we assemble them and they're ready to go in no time at all.
All right, Mitch, I can wait to offer to our customers.
Yeah, no problem. That's great. One thing one thing I'd throw on real quick on the software stuff I wanted to say is, so actually none of our software has any licensing or support licensing requirements. You can download it right now and start playing around with it. It's ready to go. Additionally, we offer calibrations for many of our things that are NIST traceable. So yeah, we're here.
Right.
We're here to help and solve the problems that you have.
All right, Mitch, thank you.
Uh-huh.
I have a question, Mitch.
Yeah.
Besides the USB-C applications, could you tell us a little bit more some other applications that we could be easily adapt to these kind of products, talking about the MTM modules?
Yeah, so the one that comes to my mind immediately is our newest module, which is the load module here in the bottom right. And where that becomes beneficial, like our whole philosophy is getting everything in the fixture, small size and things like that. So if you have motors, you may not necessarily want those motors in your fixture, or if you're doing something where they may interfere with your other items, you can use this MTM load board in place of that, so you can simulate the motor currents of your system. So it just kind of helps to bring it all together and help keep it really small. So that would be the first one that comes to mind.
Okay, thank you.
If you like, this is Justin Gregg from Acroname, and if you like a couple more examples, please feel free to reach out to Lance at Acroname, and we can work through a lot of specific examples that will be applicable to your types of DUTs. We've done projects all over the world, from everything from like high voltage consumer products like circuit breakers, all the way down into IoT devices and mobile phones. So it's the whole gambit of consumer electronics, automotive electronics, healthcare electronics, pretty much everything you can imagine.
Thank you, Justin.
Any other questions? All right. That sounds like a no by the silence of crickets.
I think they are a little bit shy. Maybe you can also write the question in the chat so we can answer.
Yeah, that'd be a great solution, especially if you want to type one in Spanish as well, if you feel more comfortable that way, and then we can have someone translate it.
Pueden poner también las preguntas que tengan en español y Mitch se las va a contestar.
So just one question, this is Adolfo. Would you send Ranza or Rebecca? Would you share this information with us? You have my email address, right? Okay, thank you.
Yes.
Yep. So
Yes,
as far as I understand, we'll be sending this to everyone registered. It'll also be uploaded to YouTube and online, available to watch at another time if I was speaking too fast.
Okay, no, thank you.
Mm-hmm.
So meanwhile, if you have any question, you can put it on chat in English or Spanish, in whichever you want. And meanwhile, can you please help us with a survey that it will not take more than 2 minutes. It will not take more than 2 minutes, and we will share it to you via chat. Here we go.
Mitch, I have another question.
Okay.
Yeah, in one slide, you mentioned about that the test of the USB hub. You was testing the CarPlay functionality.
Hmm?
Yeah, that one of Daimler. So my question is, what kind of model you was using to to test the CarPlay? Is only the USB connection, or you have to add some other functionality to the module?
Yeah, so Justin, this might be one of the best ones for you to jump in, but
Sure. Yeah, it's a little hard to explain just in a short, concise way here. We can certainly go over it in more detail with you in person. Just a quick summary is the requirements for CarPlay testing were associated with only one port of the device. And that one port of the device was routed to a couple different areas through a custom test point and carrier board, which is an integral part of a lot of our systems. And that test point carrier board allowed it to route to an MTM IO serial module, which was acting as a device in that case, and was able to emulate the switch to host that CarPlay requires. That is a full functional test of both host and device USB systems, including high speed. And so the test system was checking for proper enumeration of that, that hub and device through the Brainstem MTM APIs. The system is also capable of future-proofing itself against USB 3 advances. So if and when this module vendor decides they want to support USB 3, that test system actually routes all the USB signals also to a pass-through connector. And that way the system can be used for validation testing of USB 3, but also for production testing for USB 3 with no changes to the fixture. And this is actually, this test system is actually being marketed by our European partner. Their name is Kennigan. And of course, if you want their contact information, if you want more information about this specific test system, it is actually available as a fully ready to go product.
in addition to that, we wrote a very detailed white paper on this that may be worthwhile to pass along with this presentation, that goes into the specific details of how we did more on that.
Yep, just shoot us an email if you're interested in that.
So another question, Mitch, maybe it's in your roadmap, but I don't know if in a future you are trying to design, for example, for IoT devices to test the Wi-Fi or the Bluetooth connectivity of the devices. I don't know if Acroname it's facing out that kind of challenges, or it's too lot. It's a lot of.
Yeah, so we don't directly have anything right now for Wi-Fi, but we have done Bluetooth in the past. It's not currently part of our product specification, so it's not really in our plan. So
just to keep in mind that there are a lot of MicroFCT approaches that can be applied to Wi-Fi and Bluetooth testing, and cellular testing. In fact, the entire concept of MTM was designed originally for a cell phone RF test system. And we have hundreds of thousands of MTM-like systems deployed in China doing cell phone testing. Like that's where this concept was born. And that particular customer saved unknown amounts of money, hundreds and hundreds of millions of dollars in scaling their production systems, and in particular on their board level RF test line.
Okay.
And the only bit I even add to that is, like, RF is something we definitely keep in mind we keep a lot of things in mind, but RF is for particular our programmable power supply. There are actually two separate power stages in there. There's a linear power stage, and then there's also a switching power stage. So if you're in an RF environment, the switcher is probably not going to be the one you want to use. So we've definitely taken a lot of these types of considerations into play.
Okay. Which... Hello?
Yeah.
Yeah, okay, I think there are no more questions. So can we address to the final slide?
Okay.
So perfect. If you have more questions or do you want to know more about the services of iBTest or the services and tools by Acroname, you can also follow us via LinkedIn, Facebook, Instagram, or YouTube. Here are the users' names for both companies. And here in the chat, I leave you also the Acroname and iBTest emails for more information.
Yes.
Okay.
Please bug us.
Right.
We'd love to hear from you.
Alrighty.
Okay, perfect. So thank you
Thanks.
so much, Mitch, for your presentation. You did great. And thank you everyone for joining us.
Yeah.
Thank you.
Good job. Good job. Great job, Mitch. Thank you, everybody.
Thank you very
Thank
much.
you.
Thank you, everyone.
Thank you a lot.
See you
Mitch.
next.
Promise.
See you soon.
Yeah, please feel free to reach out anytime.
Thank
Thank
you,
you.
Mitch. Bye.
Alrighty. Alrighty. Bye.